All right, Mr. Jern here again, and I am here to explain AP Physics 5J explosions. Now, you might be wondering what's with all the talk of energy in our momentum unit. Well, it's very important to compare the two. They work hand in hand, but they're not intuitively they're a little confusing when you look at them both together because they don't always I guess, behave as you might expect, especially on your first go through this, when you're first looking at this. So it's important that you look at them both together so you can see the differences in how things work. So you're going to see energy mentioned a few times, and that's good. Very useful. So we have Angela and Carlos. They have identical masses, capital M, and they stand on identical light carts, meaning we don't count their mass at all, with bearings with negligible friction. So there's not going to be any friction involved. No work done by the carts or friction here. Carlos holds a heavy ball of mass M. That just means that heavy just means it's going to be noticeable. It's not going to be negligible. So it doesn't mean like gigantic. It just means it could be gigantic, but it just means that it's going to be noticeable. Mass lowercase m. Okay, that kind of typically indicates it's going to be less than capital M, but it's not that important. It's just know that it's noticeable. It is non-negligible. Okay, at time t equals 0, so at the very beginning, we don't care about what happens before, but at the very beginning, time t equals 0, Carlos throws the ball so that it has a horizontal component of velocity v while it's a projectile. So he might throw it at an angle, but we don't care about that angle. We just care that it has a velocity v horizontal. At time t equals capital T, Angela catches the ball at the same height from which it was thrown. That's important because that means that it hasn't gained any, there's no gravitational potential energy involved, a change in gravitational potential energy as she catches it. It's the same height, so we can kind of keep this somewhat simple. So which equation for part A, which student moves with a faster speed for time t equals less than capital T? So for the time before Angela catches the ball, essentially. Explain your reasoning qualitatively I've read it wrong. I apologize. For t is greater than capital T, explain your reasoning qualitatively without manipulating equations. Now what that means is don't include equations. You can include variables, as you can see here. Simple equations like MV is fine, but don't go like trying to derive an equation and show this is the mathematical reason. They want you to exactly what it says, qualitatively. So who has a faster speed? The answer is going to be Carlos. And you might think, wait a minute, he threw the ball. Shouldn't she have the same speed? Because there's no external work being done at this time, as far as we can tell, right? I mean, maybe you're thinking that. She catches the same ball he just threw. Why would he go faster? Wouldn't they go at the same speed? But you forgot something, and this is very common to do. She catches the ball, okay, which means she is moving along with the ball. So her mass and the ball's mass is moving to the right, while just his mass is moving to the left, okay? So that's what this paragraph is saying here. Carlos has a faster time because the original momentum of the system is 0, okay? The final momentum and the momentum every time in between has to be 0. So in other words, they're standing still at first. Velocity of everything is 0. No, Carlos is not moving, Angela is not moving, the ball is not moving. 0 velocity means 0 momentum. So as they're moving apart from each other after Carlos has thrown the ball and Angela has caught it, they'll be moving in two opposite directions. But Angela and Carlos both have the same mass themselves, but Angela has the additional mass of the ball. So therefore, while Carlos's momentum and Angela plus the ball's momentum are the same, because Angela plus the ball's mass is larger, their velocity has to be smaller than Carlos's. Okay. Part B, this is where you get to try deriving equations. two expressions actually. There's two. So it gives you 6 spots, 3 spots for each equation. They want Carlos and Angela's final speed. Okay, so start with the premise that, because we're talking mass and velocity, so we're talking momentum, that the change in horizontal momentum has to equal 0. That's what the X stands for, the horizontal momentum, because the ball is going to go up and come down. That's also going to, well, we're just focusing on Carlos and Angela because they're moving horizontally. So what is moving? Well, the mass of, we're talking about just Carlos because we want to figure out Carlos's final speed. So V final for Carlos. His initial speed, so the velocity of initial for Carlos in the X direction horizontally, plus the momentum, the momentum, which is the mass times the velocity initial of the ball in the horizontal position direction, is going to equal those two again in the final. The initial total momentum of Carlos and the ball is going to equal to the final momentum of Carlos plus the ball. And since they initially are not moving, their momenta has to be 0. And so this whole left side of the equation is going to be equal to 0. And so you rearrange that to solve for Carlos's final velocity in the X direction. Okay, that's what that comes down to. So you'll have to do a little algebra here. Angela has a similar thing, except while Carlos, the mass of the ball is separate for, they're going to have separate speeds at the end for Carlos because he threw the ball. So these are going to remain separate. But what happens with Angela is the ball is coming at her with a non-zero velocity. She has a 0 velocity, and so this is not going to go away on the left-hand side. Additionally to that, her mass and the ball's mass are going to combine and go at the same exact speed once she catches the ball. Okay, do you see the difference there? Initially, Carlos and the ball up here are both moving at 0. They have no velocity, so their total momentum is going to be 0 before and after. And when Carlos starts moving away, the ball is also going to be moving, but at a different velocity. You can write it this way down here to start with for Angela, but realize that their final velocities will be the same. So that's why, even though it says velocity final for Angela in the X direction, that actually includes the ball because she's going to have the ball with her. So that's this, you could say A plus B if you wanted to down here instead of just FA to indicate it's Angela and the ball. They're both moving together. Okay, so once you do that, you do the algebra to rearrange this equation, and you find that Angela's velocity is going to have this additional mass on the bottom, which means that she's going to have a lower speed than Carlos. Okay. Backside. Part C. Explain how your expression in Part B supports your reasoning in Part A. Well, as I just said, Angela's speed is going to include that additional mass of the ball on the bottom. In this case, it says the denominator in Angela's equation is larger because of that additional mass, making the value of the speed smaller. Part D, okay, this one, very energy focused. Okay, we were kind of talking about velocity and being able to use momentum before. Momentum was there because mass times velocity. We use momentum up to this point, but now we're talking energy. Okay, direct comparison. And it wants to know the mechanical energy of the Angela Carlos ball system. So all three together at all times. E sub 1, energy 1, is before Carlos throws the ball. So they're just standing there, not moving. You know what's going to happen here. E sub 2 is the mechanical energy while the ball is in the air. Okay, time is greater than 0, but less than the final time. And E sub 3 is essentially after Angela captures the ball. So being able to even read this prompt might have been confusing to you. So there you go. Sometimes it helps to maybe sketch a timeline to understand what they're talking about with the times. Maybe list what's happening at each time. So if this prompt was confusing to you, then list it out. Somehow come up with a timeline that works for you. And if you don't know what works for you, try different things. That's the point of these worksheets, is to practice it and find out what works for you. Okay, so knowing that, the very easy one, the lowest amount of energy is going to be E1, E sub 1. Before anybody has done anything, they're all just standing around. Their energy is literally 0, no kinetic energy, no mechanical energy. Okay, and you might be like, well, wait a minute. Where'd the energy come from? Aren't they a closed system? Angela Carlos ball? What's doing the outside? Aren't all these forces internal? It's a little tricky because think of it this way. If they're on a skateboard and they're just standing there, let's say Carlos skateboard earth system, there's no energy being inputted, right? So they're just going to stand there and not do anything. They're going to have no mechanical energy. But what happens when Carlos pushes on the ground to get going? Nobody came along and pushed on Carlos, right? So is that an external force? Because now suddenly Carlos is moving and nobody came around and pushed him. So the answer is yeah, that actually counts as an external force. When you're on a skateboard or something like that and you apply a force, in this case, Carlos is applying a force to the ball. Now, how is that an external force? Well, think about it this way. Where did he get the energy to do that? His food. He eats food. That energy is stored in him as chemical energy. I'm getting a little outside of physics for now, kind of. But that energy is stored in him as chemical potential energy. Okay, that's not part of our mechanical energy as we've been talking about it. So now what happens is this external energy force that was his food is now inserting energy into the system. Okay, so think of it that way. Think of it as if he is he's inputting energy from his stored food. Okay, I don't know if that makes sense, if that helps, but that's how it went. So the energy came from somewhere. It's the same thing as like a motion cart. When you have two motion carts together and you push the button and they spring apart, the momentum stays the same. The momentum is conserved. They still have zero momentum when you add them together, but they definitely just gained a bunch of energy, right? I mean, there's an external force there. When you push the spring in there, you pushed on it. The fact that it wasn't used right away doesn't make it any less external. Okay, you see how this is going here? Okay, so now that said, I think you could probably understand this a little bit better. So again, the lowest energy is when they're not moving because they have no kinetic energy at all and they're not going up any hills and whatnot. Then E3 is the middle one. That's after Angela has caught the ball. And why is that? Well, because if Carlos added energy to the ball to get it moving, Angela removed energy from the ball to stop it. And what do we call adding and removing energy from a system? Work. So work is being done on this system, the ball specifically, the ball part of the system, but the ball is all part of the system. And so Carlos adds energy to the ball, which is why E2 has the most energy. The ball is flying through the air. Carlos is moving to the left. Angela is not moving yet, but that doesn't matter. And then E3, because now Angela has captured the ball, caught the ball, she slowed it down. Not completely, because now her and the ball are still moving because of conservation of momentum. But the energy has been taken away a little bit, removed from the system. And finally, the lowest was when nobody was moving around. If it helps, this equation is down here. These equations, you could think of it mathematically if you'd like to. But I think the explanation I just gave you probably is sufficient. And it's sort of summarized, well, it's summarized right here. All right. These checklists are very important. When you explain something, don't assume. You could assume a couple like minor things, but make sure that you actually explain the entire thing. So you have to state these laws of physics. You notice how mechanical energy, the work is mentioned. Okay, so make sure you mentioned, like, use the vocabulary. Okay, don't assume that, oh, you know what I'm talking about, right? Wink, wink. Okay, that's not going to work. You had to fully explain yourself without being too verbose, and assume that they're your age and they understand basic physics. Okay, so still explain everything, but don't go too crazy. Like, you don't have to explain the basic laws of the universe, just explain the ones that you're learning about. All right, well, I hope that helps. I believe that's it for, yeah, that's it. All right.